The problem with the subject is that, blessing, and the problem, large parts of it were developed by mathematicians. And, they have their own needs and goals and languages, etc. So it can happen that something that you really badly need is totally unintelligible because it's hidden in math literature in some weird way. So for example, the foundational paper that I'll get to this was a paper by Stephen Smale, who described what happens if you take if you have dynamics which has initial ball of points that gets stretched and folded into a horseshoe. Something that he visualized himself while hanging out on a beach in Rio. Inside. By the time it became a math paper of 60 pages, the abstract says, consider a diffeomorphism of blah, 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 and blah, 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 and blah, blah, blah. And, I have the abstract actually quoted in the book. And you would, not in 1,000 years, think that has anything to do with lizards in that lab across the world. But it does, So I'll just use a few words and I probably won't use them very much again, but just because you'll run into them. So to describe flows a little bit more precisely than so far. What is it called? So it's a family of maps that take the manifold and map it into itself. And its parameterized by time. Now, that might seem obvious to you, but not so far in the future. We'll be looking at mappings that are parameterized by a number of such numbers, because if we have symmetries, there'll be more than one time, of course, but it is just one parameter. And it should have the usual properties. If nothing happens, so there's an identity. So when t equals 0, I have an identity operation. The flow doesn't change anything. Next thing is that if I apply my rule for time t prime, I start at x and I get to a new point in the state space. And now I apply the same rule for other t. That should be the same as prime. Starting with the point, saying that I only have one rule. Composition of two laws doesn't give me new law. It's the same law, it's just parameters. Law is eternal. And mapping x and e into point time delta. In other words, mapping my magical times one-dimensional parameter group. And it's continuous. And I've written this in a book, but I worry about it because I'm not sure it's necessary, for example, when I think of billiards. So I'll leave it to you to correct me if I'm wrong. So basically we don't want the flow that, we have a neighboring points and suddenly they get cut, slashed, and sent to very different points. We want to have at least continuity, if not smoothness. Then we will often find it useful to use a simple notation for this. So we will write this as a functional composition. That's just notation that basically, doing an operation, so you have a calculator, compute a number using the program, and you get a new number that gives you that, and then use the same program to do it again. That's an iteration. Instead of having zillion brackets, it's convenient to say, apply the function, or result, and that's what this means. Then the very important thing about flows is that they're continuous. So it's natural to look at the infinitesimal action of the flow. So if I'm at time t and I let little tau time t later alone, this by definition of how the flows act can be written as action on where am I at time t, and then time t later. Now the flow is doing something like that, and at time t, this is time tau later. So I can linearize the flow here and define the tangent of my trajectory at every point. So I can look at Vx, e tau, time derivative. And that, if my point is in d dimensions, that's a d-dimensional vector, which I will denote by b, meaning that it's some kind of generalized velocity. So infinitesimally, a flow is specified by a field, meaning at every point in space, I define a vector field. And then the trajectory is an integral through this vector field. So, all the dynamical systems that you know about, for example, Hamiltonian systems, I can write this state space vector that's the same as state space, so it consists of configuration Q1 position T, and that's called Hamilton's equation of motion, and that's because anything that, in dynamics looks like that. So this gives us the local direction, two dimensions, direction of all. And the magnitude of this thing is speed, local speed. And now, the way people visualize it, to think of a manifold as a three-dimensional curved surface. And it's a manifold. And you find at some point on this manifold, then this vector depends where I am. There is a tangent vector to the manifold at x, which is three-dimensional. I can define tangent bundle of a manifold is the union over all points of the manifold, and then each one of them in the tangent field. So the way that dynamics is defined in infinitesimal is that at every point in the d-dimensional state space, there is another d-dimensional state space attached, which is the tangent space. And the dynamics is described by totality of this vector space defined every place on. So if somebody says tangent bundle, that's what I mean. They also might like to think that when you have a integration of vector fields as you move around, and you have this vector field over tangent, what we call a trajectory, or if it's closed or infinite orbit, they might call it a fiber. So somebody else will tell you that you're interested in a fiber bond. So anyway, I will try not to use this language at all, but in the literature, this is what you'll run into, and there are good reasons why mathematicians and mathematical physicists, quantum physicists, I like to use this language, and it's a good thing. But as far as we are concerned, all they're saying is that there is state space, and instead of what we have done so far, we have described the space, dynamical systems, state space, and the map. This is a family of map at each point. One can also describe it by a tangent bundle, meaning state space and its tangent space at every point. That's equivalent description. So now if you're given this kind of local description of your dynamics, you can go and revisit the things we've done already. So for example, if you happen to find a point where the vector field is zero, d-dimensional, this is d-dimensional vector, that will be the equilibrium point. because locally you don't move any place and you never move, and that's it. So this manifold will actually have points in which the tangent will just vanish. And that'll be very important for understanding general geometrical flows. However, if B is not zero, then we'll be able to integrate this equation. Keep moving to the next tangent, and you can explicitly construct a trajectory. And you now be slopy because every trajectory has to be labeled by a point on it, but writing this x0 is tedious. X0. What is that? It's an integral of this thing. The trajectory is an integral of the velocity of the field, and as this changes on the manifold. In general, this d-dimensional velocity that depends on where you are on the manifold. That's a trajectory. So now there is something that's totally intuitive to fluid analysis, and for some reason, it's never intuitive to me. It should be obvious, so I'll say what it is, and maybe it's intuitive to you. Whenever you have dynamics, there are two visions of it. One is called Eulerian, and one is called Lagrangian, the other one. And the intuition comes from three-dimensional fluids from 19th century, where they developed fluid dynamics. But it's true for any dynamical system, because what dynamical systems and fluids share is they share an assumption that every material particle is indestructible. So when you have a point, you don't remove it or add it to the system. It's being moved around. And that's what the dynamics does. It says, you have any state of the system has its unique trajectory. And that's it, it's not added or created. For that you need noise or some other thing, but deterministic dynamics doesn't exist. So the vision of Euler is to say, I just care about what the state of the system is now. So Eulerian. I just want to know where I am. So I need to know where I am, and then I need to know the vector field at that point. And then I know everything, because I can integrate it. So, for example, fluid dynamics equations are written as equations for velocity, because that's the only thing you need. You don't care about what this material particle is, where it came from at this instant. Just specify what the world is now. So here. So the picture is just given manifold. And all there is a field, it's like a blade of grass. Define any place. And that's all I need. Because this tells me what M is, and this B tells me what the rule of the dynamics is. Lagrangian vision seems very complicated. it's sort of motivated by continuum mechanics, but it says, if I start with my initial volume instead of all spaces, then time t, I'll have another thing. And Euler only cares about what the field looks on the other thing. But Euler cares where you came from. So Eulerian coordinates say I'm just at this point, and that's what it mostly does. Lagrange says I started here and I went over there. So Lagrangian world is like a bowl of spaghetti. It's you don't look at points, you just look at bundle of all possible trajectories. Now, because dynamics is deterministic, everybody has unique future. Spaghetti don't appear or disappear, they're all there. So the world is filled with the spaghetti. And you might wonder, why would you do that? Seems totally stupid, very complicated. But the point of the whole game is that, what Euler gives you is just equations. So they give you some equations. Now, you're used to some of the equations. Some of the equations you can write on. You can write on a Young-Mills field or something. It takes 27 symbols, and you've written the equation down. Somebody asked you, so what? Now, so what is what happens? What are the solutions? So the Lagrangian vision it talks about all possible solutions of your dynamics. In particular, we'll be interested in variance sets, etc., and they'll be in this Lagrangian world. So even though equations look very enticing, it's almost never possible to know what the world looks like just from the equations. You really have to solve them. And that's Lagrangian world. Suppose you're experimentalist in fluid dynamics. What you actually measure is you sprinkle some dust into a turbulent flow and you measure this Lagrangian trajectory. That's actually your data. That's what you actually see. Now, theorists torture and force you to take your data and make numerical derivatives and produce these velocity fields because theorists like to look at this picture. But actually, it degrades the whole thing, and the whole content of the theory is actually in what you see. So a Lagrangian thing is not stupid, it's just difficult, but it's actually what you care about. So, you have local equations of motion. The general way of separate assemblies is that you need this solution. And even in experimental setting, you actually only see the solution and you try to intuit it all, but the data is solution. So it's not so crazy, it seems. And almost on this the first chapter. This will take the usual course. So the first few lectures will look totally obvious, and at some point we'll start scratching it out. This is still within the range of what we can see. So, the last remark, which I don't know where to put, but, it has to be said someplace. Somebody hands you an equation, and, maybe they do this in 13th century China, and maybe they do this in 18th century Italy. It's not guaranteed at all that they'll use the same notation, same coordinates, same, lingo. But they will be describing the same phenomenon. And the simplest version of this that you often use yourself. You sometimes find it convenient in electromagnetism or some other, but you to go from Cartesian coordinates to cylindrical or whatever. So you're used to this idea that you have freedom of choosing your coordinate system. But this actually is an enormous freedom. It turns out you can describe the same law of nature, same dynamics, in infinitely many different ways. So that suggests that you should be looking for some invariant, things about that. And in particular, if you're given your mapped out your state space and your coordinate space. In somebody else's coordinates, in the vector coordinates, intelligence and chosen zero phenomenon is not better than, let's say. The same state will have totally different labels, and it can be embedded in a totally different states. So what you need to know is you need to know what is the relation between these two things that are sometimes called integers. So what you need is some description in which all the new coordinates, I have one-to-one relationship, so I can define also. But this is some totally arbitrary nonlinear function. And you want some obvious things. This nonlinear function should be nice. So for example, in a smooth region in your original coordinates, you don't want to slice it into little pieces, but having some discontinuous mapping.
The second one should be x equals h equals y, right?
Yeah. So now you might ask yourself, okay, so this is the relation between the two state spaces. What's the relation between the two rules of motion? So if in the new coordinates, the rule of motion is this, then how do we get in the old coordinates? Well, we first go to x. So we replace this at h minus 1 y. Then we apply our motion in the old coordinates. And then we go back. So whenever I have a original rule of motion, the new one is obtained by conjugation by this nonlinear combination. So this you recognize this from the linear example, because you know that in linear, when you just have made it linear linear transformations, you rotate into the old coordinate transformation, you apply a thing, and you rotate it to the new one. But this is true for any nonlinear thing. And now you might want to know what is, this is the finite time version. Now, I don't have time, but it's in the book for what is the new velocity. So how do I go from v of x to new velocity? And that's very cute. Basically, locally, every nonlinear transformation is like, taking a piece of rubber and stretching it. So there's some Jacobian. So you will just find that the new velocity, the derivative is just like that, but it's a matrix. Jacobian times the old I. And you'll have to put in the correct coordinate determinacy. It turns out the local description is very, very simple. Going from one, you only need to know the local Jacobian of your nonlinear transformations to go from old velocity field to the new one.